Hello everyone, good day. My name is Muhammad Iman Karmawijaya. Today, I will present our research in battery management system. Our research is development of remaining useful life prediction of lithium-ion battery using genetic algorithm, deep learning, neural network hybrid model. When battery capacity drops to more than 80% of the initial value, the battery has reached the end of its service life. The remaining useful life is defined as the time at which equipment performance first arrival time drops to a failure threshold. It represents the period from observation to end of life. End of life refers to the time and number of discharge cycles when the battery characteristic parameter reaches the replacement threshold. Remaining useful prediction using artificial intelligence can be using method such as artificial neural network, support vector, logistic regression, Gaussian process regression, random forest, etc. In this research, we are using RVL prediction using a deep learning neural network combined with genetic algorithm. There are advantages and limitations for predicting remaining useful life value. For artificial neural network or genetic algorithm, there are major advantages such as high accuracy, highly capable to capture the nonlinearities, and easy to implement, both in hardware and software. There are also a major limitation, such as modeling is complex, especially for model having a large number of hidden layers and many input features, time consuming, and also need a large amount of training data. Thus, large memory requirement to store the data and algorithm. For this research, we are using data source from NASA battery from the Prognostic Center of Excellence. So this dataset contain many data from the NASA battery PCOA dataset. The data contains 4 battery in typical same type. The data contains charge and discharge cycle. For example, for the charge data, it contains voltage measured, current measured, temperature measured, current charge, voltage charge, and time. And for discharge data, it contains voltage measured, current measured, temperature measured, current load, voltage load, time, capacity. The data then extracted using data extraction method. So for each data, we are capturing the data. For example, for the battery terminal voltage and time relationship, we capture the time and value when the value reach the constant voltage. And for the battery output current and time relationship, we capture the condition for the time and value when the current start to decrease. And also for the other data, for example, battery temperature, we capture the maximum value of temperature. And in current, we capture the current when it start to decrease, and also for the voltage we capture the time and data when it is in a maximum value. And using the same method, we capture the feature. Then we can get 21 features for this dataset from the battery massa. And then we can select the feature using feature selection method. For example, we can use correlation matrix heat map to get the features that has most correlation with the capacity that are used for the remaining useful life prediction. For the neural network or deep learning network, we use configuration like this. So there are 21 input layers, and then there are hidden layers and one output layer that is remaining useful life. So in this research, we are trying to find the best hidden layers and the number of neuron in each hidden layers that resulting in a very good result of remaining useful life. For a genetic algorithm, we can calculate, for example, the first is feature selection, and the second is deep neural network parameter tuning, such as network optimizer algorithm, activation function of the hidden layers, number of hidden layers, and the number of neurons in each hidden layer. In this research, we only tune the number of hidden layers and the number of neurons in each hidden layers. So we designed the chromosome for the genetic algorithm. In this slide, I display that the chromosome contain the number of hidden layers for each hidden layer and number of neuron for the hidden layers. To simplify the research, we limit the number of hidden layers from 2 to 10, and number of neuron in each hidden layer from 2 to 80. In genetic algorithm, we can use performance evaluation or fitness function to get the best result for each population of the genetic algorithm. We use the root mean square error, mean absolute error, coefficient of determination, and index of agreement. The parameters for the genetic algorithm, we use number of population 30, number of generation 100, mating pool size 24, mutation rate 0.5. Okay, this is the design for the genetic algorithm crossover and mutation. So if the mother and father, the chromosome for mother and father is different, we can get the child chromosome using this method. And after the mating process, we can use the mutation to get the best result in each population. Okay. So the result, we get the result using the 11 input deep learning neural network and 21 input neural network. So the 11 input neural network is selected to get the comparison between if we use all the features from the feature extraction above, and if we use the feature selection, only a specific item that run into the genetic algorithm. We get the performance evaluation, R square, mean absolute error, root mean square error, and index of agreement. From this graphic, we can see that the value of fitness function the value, for example, for the mean absolute error is decreased each generation. It means that the maximum minimum absolute error is get optimized every generation. The same result also happened to the root mean square error, where the value of RMSE decrease each generation. Some generation it get to the value is increased, but overall it decreased from the first generation. For the R square and IA, the value, the good value is when the value near the point, the value of 1.0. So the index of agreement and R square are increase if in each generation. It overall it will get to the value of 1.0. In this chart, we also see that the 21 input of neural network and 11 input of neural network quietly different. So the 21 input 21 input neural network have a better result than the 11 input. And we can also see the result in representation of deep neural network parameter using the spider chart in the left side. And also when we use the model, the result model of deep learning neural network to the test data, we can see that the result is quite good, like this. So the conclusion is the main achievement of this study is to provide an efficient genetic algorithm, deep learning neural network hybrid model in predicting RUL or remaining useful battery. The model has the ability to self-evolve to find the optimal model structure, where the optimal number of hidden layers can be treated as a variable and discovered using the model's evolution, beside to the other important parameter. The result show that there are two models for 21 input genetic algorithm deep learning neural network and 11 input genetic algorithm deep learning neural network, with result quite same but better in 21 input genetic algorithm deep learning neural network. Then we can also optimize the genetic algorithm using parameters such as network optimizer algorithm and activation function of the hidden layers, beside the number of hidden layers and number of neurons for each hidden layers. Okay, thank you. This is our presentation. Thank you for your attention.